All
right, thanks for this chance to speak. This is mostly a talk for the suspensions people because this topic I have snuck in, like Romain did yesterday, one-word memory somewhere so that we can think about it a little bit. And I've also tried to, knowing that some people from the memory program are in the audience and not just suspensions, tried to start a little bit at the beginning. So this is a picture of my annular granular rheometer, so the top view. And you'll get to see all of these different features of this during the course of the talk, but essentially the center rear shield, this is about 5,000 particles around there, and the feature that I'm most proud of was cut by Ted Brzezinski, formerly a postdoc in my group, and he used a laser cutter to cut all of these little leaf springs, okay, which means the whole wall can breathe. Okay, and what we'll see is this gives us some rather unique capabilities because we can get torques from the motor, and we can get both normal and tangential stresses at the walls, which are usually something that's tough to get from experiments. Okay? And the experiments I'll discuss here are mostly by my grad student Ju Tang, and there's been a lot of conversations with my collaborator Michael Shearer at NC State, and then Natalie Vreen's about to arrive tomorrow. And you should pin her down and have her tell you about some of the stuff that we're continuing on from this to do with her and her grad student, Amalia Thomas. And I'll allude to that at some point during the talk. Okay. But that data is pretty raw and exciting, and we're not quite ready to stick it up on the permanently recorded screen. All right, so for those of you who are coming here from the memory program and maybe haven't thought about this, so little quick introduction to granular rheology. It doesn't really do justice to the whole field, but at least it'll get you the vocabulary so you can get through the talk. So commonly, something that's been very successful for a number of years now is, where's the laser pointer on this? Yeah. You know which one's that one? Oh, cool. All right. Is to talk about the inertial number for a flow. Okay. And so this is the shear rate, gamma dot, the particle diameter d, the pressure, confining pressure on the particles, and the density of the particles themselves. And you can think of this as a ratio of two timescales. So the purple ones are the microscopic timescale, so how long it takes to squeeze a particle into a hole of its own size. And then the inverse of the shear rate is a macroscopic timescale of deformation. Okay, the larger I is, the more rapid the flow is. Okay. The other useful number is the stress ratio between the tangential and the normal stresses. And what we'd like to write is a relationship between these values. That is something we can understand both from physical principles, why it arises. And then I should mention this work is funded actually by an industry collaboration, IFPRI, the International Fine Particle Research Institute. And so they are interested because if we can do a good job of relating these two things, it allows us to do better engineering. So we could have something like a Navier-Stokes equation. Okay, so a local rheology would say that it's very easy if you know one of these, then you know the other, and you're done. However, this doesn't work as well as you might like in some peculiar circumstances that I think are very interesting. So some key failures of that viewpoint is that if you want to look at the transition from faster inertial flows into much slower and even creeping flows, this doesn't work very well. And actually, Doug Jeromack gave us some nice ideas about where that transition really matters in Earth system flows, for instance. Another problem is that when you drive flows from the boundary, you get shear bands. And we all know that the shear band dimensions depend on both the geometry and the grain size. So there's something weird going on there, and that's been seen by lots of groups. And the last thing that I find particularly interesting is this hint that if you are applying some sort of shear vibration in one part of the flow, okay, other parts of the flow seem to know about it far away. And so things that shouldn't be flowing can be perturbed by really gentle vibrations or shear someplace else in the flow. Okay, there's a number of experiments that have seen that. This one's particularly nice. There's a great movie up on Martin's Van Hecke's website taken by Carrie Nickel, where she has a rubber ducky floating in a granular bath, and when she applies small amounts of shear at the bottom, she gets an Archimedes-like law, whereas if there weren't small amounts of shear at the bottom, it wouldn't be fluidized, and the ducky would just sit on the surface of the grains. Okay. So the local rheology, there are plenty of circumstances where it's successful, and there's a number where it's not so successful. Okay.
This last point, you didn't say everything there is to say, but why Which part of this is surprising?
It's not surprising. It's just that then we need to capture it. Right, yeah. So I would say it's unsurprising, right? I mean, it's not like we don't know any of this, right? It's just that I would say this is more of a justification of why bother going beyond local rheology, which would be much easier to do. Right. Okay, so quick thing here. So, okay, in a local rheology, this is the very quick summary for people who are new to this. Local shear rate is determined only by local shear stress. And then if you want to know the resistance to the flow locally, it only matters for local shear rate. As soon as you go to non-local things, you're going to put in things into your model where the particle arrangements in one part of flow are triggering events in some other part of the flow. Okay, so you have to know both about the local resistance to the flow, okay, and what's going on with these non-local events. So I'm going to talk about two models here. One by Ken Cameron and the other by Mehdi Bouzid. So you can ping him for gazillions more details on the theory, because I'm not going to do a thorough job of it here. But you have the local expert highly available, and I'm going to lead out the Kosarat model. The what?
Non-local.
He's the non-local expert, right? Our local non-local expert. Okay. So these are not the two names. They give their own models, but I'm going to use those because it helps me to distinguish what's a little bit different about what they're trying to capture. Aside from the fact that there's a bunch of equations. Okay, so the justification that Ken Cameron originally proposed 5 years ago was this idea that if you look at the ratio between the shear rate and the stress ratio, very similar to these numbers I introduced at the beginning, that the more it's flowing with respect to how hard you're forcing it, the more fluid it is. Okay, and so he gave.
Tell me what mu is again.
So mu is the stress ratio. Let me write these on the board.
Oh yeah, okay, yeah.
I'm going to write these on the board because we're going to use them a lot. Okay, and I'm going to write that inertial number is gamma dot d, get rid of p over rho. Okay, and this equals T micro over T macro. I goes large equals fast flows. And this is what I'm going to not talk about. Okay, and what I'm going to be talking about is I goes 1 to smaller, and this is what I am going to talk about. Okay. All right. So he posited a.
It's meant to be like a control.
It's an inertial. It's called the inertial number. So the more inertia is carrying the flow forward, right? So the faster it is, the more inertia plays a role compared to. So if you think about this as, the gamma dot, which has units of inverse time, sets a macroscopic time on which drama.
Okay.
Yeah.
All right.
Yeah.
Thank you.
Yeah.
Capital H.
And capital H, I'm going to come to in a minute. We haven't gotten there yet. That's the heavy side function. All right. Oh. We'll get there. That H. This is, yeah. So, all right. So there's a granular fluidity that comes about between the ratio of the shear rate and this stress ratio. Okay. And now we want to say, okay, if you're going to have, this is an inversion. This is not mu of I. This is I of mu. Right. It's an inversion of that. Okay. But you shouldn't have any flow if you're below the yield stress. Right? So there's a number mu s, which should have been read here, by the way. I don't know why it's not. My fault. Okay. There's a number mu s that if you are above that, you've exceeded the Coulomb failure criteria and you're flowing. Okay. And if you're below mu s, you shouldn't be flowing at all. And that's what the heaviside function is for.
Oh.
Then it says this rule, okay, is that how far you are, the further above the mu s you are, the more you flow. Okay, and there's a constant of proportionality here, but if you're below mu s, the heaviside function says, sorry, you don't get to flow at all. Okay, so that's a local rheology. Okay, and there's actually a local fluidity, okay, that comes about from plugging things like the time scale that from over there. And so this can actually, if I take this and this, I can rewrite this. So this is a local fluidity where the flow happens, again, not below mu s, but if you're above mu s and this heaviside function is 1, okay, then you get more fluidity the farther you are above it. Okay, and this would say below mu s, no flow at all, no fluidity at all.
What is capital T?
Capital T is this. That's actually my T micro over here. So I'll write that. also. Okay, so T, which I'm writing T micro down here, is this D over square root P over rho. So how far, it's a squeeze, how long it takes to squeeze a particle into a hole that happens to be available to it. Okay, so microscopic rearrangements.
How is that a measure of how long it takes to squeeze a particle into a dimension D?
Yeah, right.
All right, so you can think of it this way. If you have P over rho, that's like force over mass. That's like an acceleration, right?
The speed of sound.
You can think of it as speed of sound, right? You can think of it there's a lot of different ways to think about it. It's a non-dimensional quantity, right? It's a non-dimensional.
I'm wondering how this is relevant to a micro time scale, because the d over the speed of sound is the time it takes the sound to travel over a distance of a particle diameter d.
Well, it's not the speed of sound P would be the elastic modulus. Of
Right, this is the pressure. This is the confining. This is how hard I'm squishing at the top. So if I'm squishing this thing.
Where P over rho is the velocity, right?
Yeah, yeah.
It's related to the speed of sound.
Yeah, but no, but that's for the elastic modulus. This P is, unit-wise, you're right. Okay, but this pressure is a boundary force that I'm applying. So if let's not put any flow in this for a second. Let's leave the flow, let's leave the shear stress out. So if I just want to squish this, the harder I squish, the faster I can squish the particles into holes. Okay.
It'd be nice to be able to do that calculation, but I don't think it can be done.
It's not. And so this is just a dimensional group that has the flavor of that. Okay. And so there could be a 7 in there, and it wouldn't bother me.
Against friction, for example?
Right. So I'm doing.
You're pushing to spread the particles apart.
I am doing none of that. I am merely saying that this is a dimensional group that expresses that idea. And there could be a 7 in here for all. A 7 in front of it for all I cared. Right. Right. It's just this is think of this in sort of a Buckingham pi sense. That these are the things that control how fast that happens. All right. So inertia does matter. So inertia comes in because you have when you have I, right? If you look here, this inertial number is taking into account how fast it's actually going. All right. So now we have an idea, and this is where this becomes a non-local model. Okay. So locally, if you're below the yield stress, you shouldn't have any fluidity, nothing can flow. Okay. But the idea is that, in fact, that's just a situation in one location. But any little bits of drama that happen here, okay, annoy particles across the system. Okay. And so the way that the non-local effects are put into the problem is to say that if there are, that the real fluidity is a diffusion of the local fluidity to other parts of the system. Okay, and that there's some length scale, or diffusion constant if you'd like, over which that's happening. Okay, and so if you know your local fluidity, okay, and this is where it's important to know things like pressure and shear stress and so forth, in order to be able to calculate these numbers, you can diffuse your fluidity throughout the system. You can put that back up in here. You can know your shear stress. You can solve for your shear rate, and you can go forth and predict velocity profiles and widths of shear bands and things like that. So that's the idea. The last piece you need to know is what the length scale is over which these non-local effects can diffuse. So this is a non-local length. Okay, and measured in units of d. This is a functional form that was posited by Cameron and Koval. Okay, that this is the square root of 1 over how far you are from the yield stress. Okay, there's some magnitude here, and they've played with other functions here. Actually, to the 0.6 instead of to the 0.5 tends to work a little bit better empirically, but then the units are bizarre. Okay, so you have some choices here to play with, and we've sort of taken the simplest, most. This is actually slightly different than what's in this paper. We've sort of taken into account advances that they've made in the past 5 years as well. Okay, so this idea that the proportionality of the shear rate and the stress is Bagnall type. There's some stuff added on. And the key thing is that there's a cooperativity length over which other particles cooperate with the ones that have drama. This fluidity diffuses, okay, and this gives you flow. Okay. And there are only 3 fit parameters in here. They're A, B, and μs. The rest of them are things that in a simulation you certainly can measure. In an experiment we have strived to be able to measure all of them. Okay. So there's a second model that Mehdi was integral in creating, okay, and it also says that there should be something like a fluidity field, and you're going to jump in when you say something I don't like, so we just like get it on the record that I've screwed this up. Okay, it is just like this, okay, except that there's a factor of mu s between the f and the g, okay, but they're very, very similar, okay, that there is some local inertial number, okay, that you can determine locally, and this depends on actually the same microscopic time, okay, and this is a posited form, okay, and there are some good justifications for it, but I'm going to skip those for the moment, okay, and that you would think, okay, and again, this is the definition of the inertial number, comes from gamma dot times time, okay, but then that is allowed to have a diffusion of fluidity, okay, and that if you tried to write bet I of mu to better and better precision, okay, you would add Taylor series terms to that, okay, and this is now a gradient expansion, okay, on doing a better job of writing your inertial number, okay. So both of these models have a Laplacian. Both of those Laplacians tell you about the diffusion of fluidity. One of them says it comes from a cooperative effect. One posited that it came from a gradient expansion, okay. These are both perfectly good ways to think about it, I think, okay. And what we're going to find is it's very difficult to distinguish the predictions of these models, okay. And from that, okay, we'll get on from there, okay.
Okay.
Yeah. That's what Mehdi first.
Yeah, if I may say,
please.
Two things. So the main difference between Cameron model and our model is our fluidity is exactly the inertial number.
Yeah.
So
Which is very
stresses,
convenient.
Yeah, the stresses is not included in this fluidity.
Right.
So the second thing is, so if I may correct, is the fact that you have written that there is 4 fitting parameters in our model. So we have exactly 3 fitting parameters. So this length scale.
So which one should I strike from the list?
Is L. So as soon
So
as
the little L I should strike from the list. Okay.
So this one you get from your simulation, and you calibrate
Okay.
this length scale. So when you calibrate it, you get mu of L, and this is only the fitting parameter that you have in your simulation.
Right. In
So
an experiment, we had to fit it. In the experiment, we had to fit it as well. So in our experiment, we had to fit all of these.
Yeah.
But if there's a way around it, we should talk afterwards, and you can tell me how to not do that. But we had to fit each of these independently. We didn't find a way to fit them separately.
Okay.
Yeah. So we did. And there may be something that I'm missing that we could be doing that's cleverer. Okay. But so I'm saying this is now me as an experimentalist speaking, right? That these are the numbers that I don't know, right? Every other number up here, pressures and densities and shear stresses are things that I have measured. And I have no problem reporting with error bars. These are things that we had to, go and fit. Okay. And so from that, and I think that's all I mean by that 4 is that we had to fit them. Yeah.
Can I ask you about?
Yes. Sorry, Wilson.
That these fluidity diffused. I don't see a d by dt in it. I mean, are you talking about steady state?
Steady state. This is steady state. So I'm not going to deal with.
There's always a steady state.
I am not ready to deal with transients yet. I would like to get there, and I hopefully will get there soon. But at the moment, I'm doing steady state because I'm a beginner. Okay, and both solutions, when you go through the whole model, okay, you will end up that there is a diverging length scale, okay, at mu s. Both of them have this prediction. Okay, there's a slight difference. This one is symmetric, which you can see here. Mehdi's model, that prediction is asymmetric. Okay, but they both have a divergence.
Sorry, I thought that's a prescription, not a prediction.
These are models.
No, you said it's a prediction, but the length scale divergence is prescribed in that model.
I would say that the model predicts I should see a divergent length scale in my experiment, but I might just be speaking about that. That's sort of the way I like to view things.
And what about boundary conditions?
What about boundary conditions? So far, I have not put any boundary conditions in.
And what about determination of the stresses?
We will get there. I will tell you how I do all of that. Okay.
But can I get back to Robert?
Yes.
Well, that's important because if I understand the previous question correctly, the length scale L drops out at the...
This is not the length scale divergence. It's a different one that I haven't put on here. It's a different one that's not on this screen because I ran out of space.
But the length scale that is set by our model is set by this Laplacian.
Yeah.
So once you have the Laplacian, you have the divergence.
But that's different from the left-hand side.
That's
model.
They're different. They're different. It's just that I ran out of space to put the extra equation there. Now,
Yeah, but there's a picture on the right and a description on the left.
Exactly.
yes, and there should be one more line here where I say how this capital L depends on this capital Y and US, and that actually has a square root in it as well, and it's quite similar. Yeah. Okay. So I would say, and this is me philosophically, that these are models that have been provided to the community. Okay. They have been well tested in simulations to do a good job of describing what is observed. Given boundary conditions, given all sorts of, stuff that you can know in a simulation, okay? And what has been much less tested is whether or not these actually show up as real physics in an experiment, okay? So when you go through, you have all of the information in a simulation, you can go back and say that things like the velocity profiles that are observed can be predicted by this, okay? Okay, but in an experiment, it's a lot harder to do that.
So you're telling us a simulation does not distinguish in those two models?
Not in ways that I think are meaningful.
Simulation done by the respective camps or the...
No, because
There is a
they're different.
quantitative difference between these two models. Actually, you can have situation where you can discriminate between these two models and put both prediction on top of each other and see that.
They're not the same. Yeah.
So which one is better?
Well, he's going to say his.
The right.
So let's just say that the models. These are as awful as they look. They're actually leaving out a lot of physics, right? And so you don't expect them to precisely agree with anything you measure. And the question is, which features one captures versus another captures can be subtly different, and you might care more about one than about the other, right? And so reasonable people could even disagree as to which one does a better job, right? Okay, so this is actually not that interesting of a slide. I mostly put it up here to remind myself to tell you a couple of things, is that this idea of simulations, people have done simulations, they have captured them with these non-local models, they get values for these parameters, okay? We're starting to have some sense of what the values are for these, okay? Because they seem to, in a sense, be fairly consistent across different simulations by different groups, and so forth, okay? And each of them has a physical interpretation that can go along with it. Okay, and so as an experimentalist, I look at this and say, all right, so one, talking with my industrial collaborators, if they give me a bucket of beads, or a bucket of beet seeds, or a bucket of coal, right, whatever they give me, do I know how to determine these parameters, right? So then they can do a sort of an Navier-Stokes-like simulation, right? And what you want is if you give me a bucket of beads, I do some stuff in the lab, I say these are your numbers, right? And that they can reuse them in any geometry. Hoppers, different boundary conditions, whatever. And that same set of numbers can be labeled on the bucket of beads, right? I can write on the bucket, these numbers are those numbers, and they belong to the particles. Just like viscosity belongs and surface tension belong to different liquids we know. Okay, so that's the goal. Okay. Ultimately, I would like to think that these fit parameters here are something that I could provide guidance about from a first principle standpoint. If I make my particles rounder or softer, or rougher, which of these numbers changes, right? And so that if you want to then say, I want the flow, if I'm designing something, I can then invert that process. Okay. So that is, and then the last, and so these are sort of the practical things that I think, physicists, can bring to this problem. Okay, an experimental physicist.
Karen, there's one more thing. You'd like these numbers to be the same in different types of shearing.
Exactly. So not the geometry. So if I can buy a bucket of beads, I can do a test in my experiment, and then I can take a magic marker, permanent magic marker, and write on the bucket, B equals 1, mu equals 0.8, mu s equals 0.5. I can give those bucket to somebody in another lab. They do an experiment.
A different experiment.
A completely different experiment, right? And they agree that my numbers gave them a good prediction for the flow, right? And this is not where we are in granular flow right now. Okay, we can't do this. Okay, and it's not immediately obvious from looking these. Is like, all right, so B is the number that controls the steepness of the rise of mu I, right? So like, if I make a particle elliptical instead of circular, does that number go up or down, right? Okay, I think physicists can say something about that, because how does anisotropy couple into that, and so forth. Okay, so these have been successful. You can take a geometry. This is actually the geometry we chose to use because we already had one. Okay, you have an annular granular rheometer. You can measure mu and I. These are all from simulations. And this is actually simulations that Georg Koval had done previously, and then they used this new model to explain them. Those are the data from the simulations are the points. The non-local rheology model is the line. You can get similar plots from Mehdi's data. This stuff works, right? It works. Okay, you can get the velocity profile. You can get a cooperativity length diverging. It all works. Okay. There's some challenges. Okay, so I love this plot from Mehdi's paper. It says that if you change the particles from hard to soft, the heterogeneity, so this is on whether or not the shear rate is increasing or decreasing. The heterogeneity of the flows is very, very different. Okay, and yet the non-local model can capture both of these. Okay, so these really do work. Okay, so I think the key challenges are that we want to actually test whether, yeah, Wilson.
Remind us how the particle hardness enter into.
They don't actually. They enter, this is part of what I'm interested in, is where do I stick particle hardness in those,
That's what I thought.
yeah, where do I stick particle shape, right? Like, where do I stick those, right? Okay, so first thing is, are there things we can do to test mechanisms, okay, and see if the proposed mechanisms are actually the correct ones, or they are qualitatively useful, but the mechanisms might not be what we think they are. Okay. Can we even see a diverging length scale in experiments? Like I said, most of the experiments done have just checked that the V of R, the velocity profile fits, and they're like, yay, we're great. Okay, and I'd like to do a little better job than that. The big thing that I'm excited about is what's setting these parameters, and I'll only touch on that at the end of the talk, because we're just getting going on this. Okay, already been brought up. Transient behaviors, right? Shear reversals and so forth. Stick-slip behaviors. Are these models robust enough to be able to really capture those? And in particular, and this is the one place you'll hear the word memory, if you've been shearing this in some way, how long does the model remember that? And actually, are still those simple 3 parameters enough to be able to capture those effects? So that's the token memory comment. All right, so here's the annular granular rheometer spinning. This is sped up 25 times fast because it's boring. What you can see here is the leaf springs, and if you watched very, very closely, you would see some of these moving in and out by as much as like 0.5 millimeter. Okay, that's not dramatic.
Just the grain size?
The grain size is about 5 millimeters. Yeah, about 5 millimeters. This whole thing is this big across. This big across.
And it's a monolayer of particles?
And it's a monolayer of particles, and eventually we'll get to start using photoelastic particles in here. These are photoelastic, I just don't have polarizers on, so you can't see them right now. And we'll get to that in a little bit. The initial experiments, we didn't actually use the polarizers. Okay. All right, so these are idealized 2D experiments. Everything's in a flat layer. This allows me to control the shearing. I know what everybody's doing. I can instrument all the boundaries. I can track all of the particles. I can pick whether I want my particles to have cool shapes or to be photoelastic and tell me forces, right? I can sort of pick what I want. Okay, so this is not the real flow. This is a very fake flow. Okay, and we will hopefully work up to slightly more realistic by doing things like this. Like, so what happens when you have angles and concavity and so forth. Okay, so important things about these really toy flows is that hopefully we'll get to the point where we can do first principles determination of the material parameters, okay, and hopefully can isolate what's actually the mechanism of local versus non-local things. Okay, so here's some parameters. These are, all right, so some things you need to know. We're going to particle track. We know the velocity at the wall because we set that. So our boundary condition is that we set this at a fixed speed. Okay, all we do is we set the rotation rate here. Okay, we have selected a wall with a particular stiffness so that it doesn't dilate much.
Is the inner boundary bumpy?
It is bumpy on the scale of the particles, and so it can grab the particles, and there's of course still some slip, but it's like 0.8 or something. Not 0.8. The velocity there is like 0.8 of the wall velocity. We can measure from the particle tracking. This gives us V of R. We can take, this actually is not the right derivative. There needs to be the minus V over R in front of here too. It got cut off, I guess. So we do this in polar coordinates correctly, unlike that equation. We can measure the inertial number as a function of R. Okay, we can measure the stress ratio of the shear over normal stress as a function of R. The pressure is constant from force balance because this is quasi-static flow. And you would think that because of the geometry that the shear stress would fall off as the whole, big R over position R squared. In fact, we're going to have to correct this because we have friction with our bottom boundary. Okay, so I know I have an experiment. We don't have friction with the bottom boundary. That's not this experiment. We have friction, and so we're going to have to account for a contribution of particle drag, which contributes to this shear stress. Okay, that was a bit annoying, but we did it. Okay, so the stuff you'll see in all that comes are 6 experimental runs. Okay, we picked 4 speeds spanning, several orders. That's actually 0.02. They're actually four different speeds spanning 3 orders of magnitude. Okay, 2 different packing fractions. Okay, and those are the 6 runs. So on these plots, the 6 different colors are 6 different runs. And remember, the goal is that I pick one of these and I fit the parameters, and then those parameters need to work for all of the other runs. Okay, that's the goal. Okay. All right, so we can do particle tracking and get speeds. We can take derivatives and get shear rates. We need to calibrate our walls. Okay, so I told you we have these lovely leaf springs. Okay, but we need to know how to convert their positions into actual stresses. Okay. And so we put it in instron, and we poke it by different amounts, and we poke it normally, we poke it tangentially, okay, and we chart out that as a function of the force from the instron, how much did it deform? Again, a few millimeters, okay. We will declare them linear. Okay, they're more noisy than they are nonlinear. These 4 parameters go into a fit that every time I know the position of a nose, okay, has been displaced, so we can do a little autocorrelation functions. Every time the nose has been displaced by delta x and delta y, I can figure out what its normal and tangential stress are, okay, on that leaf spring. And I've got 52 of these leaf springs going around. Here are trajectories. Here are time series of just the normal and tangential stress for one leaf spring as a function of time. And they are sensitive enough, and this is what I promised you, Karin, that we can see individual stick-slip events at the wall. So we can these are actually, force chain failures happening on the length scale of single leaf springs. So we actually ignore that. We just average, okay, because we're looking at the steady state. Okay. All right, so this is, so now we have a wall sensor that gives us normal and tangential stresses. We have torque from the inner wall, okay, just to make people happy that this all does what it's supposed to do. If we change the velocity of the inner wall, there's Reynolds dilatancy, okay, and the pressure goes up and it pushes the system out. So this behaves like you would expect. And we really do see very cool stick-slippy dynamics in there. Okay. All right, questions about that? That was experimental details was brief, but I think that was all you need to know about the experimental details.
Can you give us an idea of the range of I?
Yeah, next plot will have it. It turned out to be slower than we wanted. We actually couldn't get it up as high as we wanted.
How long does it take to reach the steady state?
Depends dramatically on how fast we're shearing. This is 3 orders of magnitude. So we do 2 hours, which is enough for all of them, except possibly the slowest one, and we don't see problems with that, so we think we're okay there too. Yeah, so these runs are a couple hours, this is a day, or 2 days of run. I mean, they're very different in their length scale, their time scales. And importantly, this is one of the reasons that we don't do the photoelastic measurements, is we can't afford to do all the photoelastic processing for all of these. And so having a boundary measurement is much easier to do. Okay, so we're going to test these 2 non-local models, see how they do. By the way, they do great. I'm going to skip to the punchline. They both do fabulously. Okay, so we're going to test them 4 ways. Okay, so one is that can we capture the shape of mu of I? You'll get some numbers in a second. Can we use that mu of I to go back and say that the velocity profile makes sense? So this is what has been done in experiments in the past. But we want to check 2 things that means that the model is a well-behaved model, which is, does the length scale diverge at mu s? Can we actually pick that up? Okay, and is there one set of these fit parameters that can do all 6 data sets? Okay, and we succeeded all of these. Okay, so test 1, fitting the mu of I data. How are we doing for time? All right, cool. So the solid line here is the cooperative model. The dashed line is the gradient model. They are not that different from each other. Okay, you might say that one works better than the other. Neither of them work fabulously on this one data set. This is the data set that we fit. So we fit all the parameters using these stars. Okay, and the reason we did that is because it's the data set that crosses from the non-local to the local regime. So we can get all of the parameters from that one. Okay. So we discover that μs is about 0.26 because for our slowest run, it maxes out about there. Okay. I will come back to this number. I'll give you two other ways to determine it before the talk is over. Okay. So already just from this mu of I, so did we get up near I equals 1? We didn't. Okay, so this is why I'm collaborating with Natalie Vreen now. Okay, so she has a different apparatus, so we can start working higher than this. So these flows are all very slow. Okay, these are all very creeping flows. Yeah. Yeah.
So it is above us, you say you local actually?
So this is local, and this is non-local regime. If there's any flow below μs, you know it was non-local.
But above US, it is non-local. You know it's non-local.
Well, I'm okay. So maybe I shouldn't use those regimes. This is the regime in which you don't need non-local effects in order to flow.
Okay.
This is a regime in which you only flow because you have non-local effects. Right? Yes. Let me be clear about that. So we did this run to cross between the two so that we could fit the parameters for a run that had both regimes, and then we use those parameters. And they have to just work on those. So every other one except this one, we didn't fit the parameters. We just borrowed them. We labeled the bucket with our permanent marker. And then we had to use them.
I mean, why should something called the inertial number work with such minuscule inertia?
That's remarkable.
We ought to give it another name.
We should give it another name. So this is, I will cede that other people have called it that. That's all I'll say. Yeah.
So I have another question related to that, which is, in my understanding, the thing we're flying below US because somewhere in the system there was something above US.
Yep.
But besides the one with the stars, all the other ones, they don't have anything above US.
They do, because locally there's places that are right next to the steering wheel that get a little bit of drama.
Okay, so these
Yeah.
are the ones.
Well, you can't, it's very tough for us to measure stuff close to the wheel because it's actually going faster than we have a camera to collect it.
Okay, so there's
Yeah. So there are some, you're going to start seeing data plotted as a function of radius where there's not data within a few particle diameters of the steering wheel because we can't collect good data there. So we didn't trust the data. It's not that it wasn't there, it's just we couldn't trust it.
They're important to induce flow.
They're important to induce flow, but then we couldn't make measurements there. Yeah.
So this μs is measured at the outer cylinder.
So this μs is actually, so this is actually the inner edge here. Yeah. Yeah. So this is the outer edge, and this is the outer edge, this is the inner edge. Yeah. Okay.
No, I'm sorry. How do you measure μs?
I don't. I guessed it here. For the moment, I have guessed it. I will do better later. Okay? So this was our initial idea was to take the largest value we saw on the slowest run and say that because it was going so slow, we know none of that was in the regime that could have flowed locally, and so that's probably approximately the number. So this is a terrible guess. This is a guess based on very little information, but we'll see that it's not as bad as it looked. Okay, this wasn't a terrible idea. But initially it was all we could manage to do. Okay, so experimental detail 1, I told you there's drag with the bottom plate. Okay, so we have to cook up a model that puts in some basal friction. This is not a full stress solution. We have done a full stress solution. It doesn't do any better than the toy model that says that there's some extra shear stress that comes from the drag out at the outer wall, at the leaf springs where things aren't moving, and that becomes less as you move in towards the inner wall because the particle packing fraction is less dense near the shear band. They have a little bit less drag, proportional to the amount of surface area in contact. Okay. We can put other things here and they do okay as well. Okay, so this is sort of the simplest model that's justified the fact that we have an exponentially decaying packing fraction, so there's less drag where there's fewer particles dragging. Okay. So we have two measurements. We have a measurement of the shear stress at our torque center, and we have one from the leaf springs. Okay, and then what we find is that just one value of a decay length and one value, it allows us to fit all of the data. Okay, this one's not a great data point, actually. But it does well enough. Better information here would come if we had photoelastic particles in use, which we aren't using yet. Experimental detail number 2 is that before this is done, I'm going to have to take 3 derivatives of my velocity profiles, which is really not that much fun, particularly when taking more data gets more and more expensive. So here's what you'll see is what we've done is that the stars here are the data points. Okay, inner wall to outer wall, and you see here I'm missing about 2 particle diameters here that we can't get. Okay, so you're going to see some data, when they're data points, that means that I use things like finite differences, okay, or sometimes in some cases Fourier derivatives, right, to get the differences between the data points. And in other cases, I did something that's a lot easier, which is this is a completely empirical fit to the data, which I can then take analytical derivatives of, okay. And so I will show you both, okay, but they're not good solutions for taking 3 derivatives of experimental data. And what's going to happen is the more derivatives I take, the more I eat away at the ends of my data. Okay, so in the end, I will have lost, well, I've already lost the inner wheel, and I'll actually lose the outer part as well. Okay, so there's only going to, so the data is actually going to be about 10 particle diameters of data where it's neither too fast nor too slow. You know, this is the Goldilocks regime. And we worked hard to make sure the interesting stuff happened in the Goldilocks regime. Okay, so we lucked out. Okay, so we can measure the granular fluidity. This is just to give a sense of what that looks like. It's decaying approximately exponentially away from the inner surface. And by this point, because we've taken several derivatives, we've eaten away, quite a large way, we've eaten away data in towards the center. Okay. So this is, the what?
You're seeing creep in the...
And we're seeing, yeah, there's flow out here. Yeah, there's flow out here because there's still fluidity out there. There's not much. Okay, so that even though it's below the Coulomb yield criteria, it still can flow out there because there's a little bit of fluidity out there to do stuff. Okay.
And for the boundary conditions on the models, you've taken the measured values of the velocity at the points in question.
Yeah, exactly. Yep. And since we've measured everything, we can do that. Yeah. So you just put it into an ODE solver and off we go. All right, so we test the speed profiles. Here it is on a linear scale. Here it is on a log scale. And in this case, we're leaving the actual velocities. In this case, we've scaled it. Actually, no, on both of these, we've scaled it by the wall speed. So 1 is the wall speed. You can see the slip here, right? You know, it's like 0.9, 0.8. We're not getting a full. We're not getting all of the complete transfer momentum from the wall because it's not infinitely rough. Okay, and these fall off approximately exponentially. Okay, it's not exactly exponentially, and those are examples of them there. So the model success 1. Success 1 was we actually got to fit the mu of i's. Let me go back and say that. Right, so remember we got the mu of i's to fit these well. You can take those values and you can check that you can fit the velocity profiles. That works as well. Okay. Diverging length scale. Okay, now this is where again we have to take 3 derivatives. Okay, we can either do it numerically or we can do it analytically on an empirical fit. And I'll walk you through this. So this is the mu s that I claimed I read off of the mu of I plot. The crappy mu s. Okay, I'm like, this is my best guess. Okay, that's the red line. Okay, the blue points are from derivatives of the data points. The blue dashed line is from derivatives of the analytic, of the empirical fit. Okay, and if you take those and you put them back into the model, okay, so right near, so here's a zoom out. So this goes over a large range, all of the data points that we trust. Okay, and the error bars are on here, and you'll see they're dramatic. Okay, so what we see is that as you approach mu s from the side where you would have flow in a local rheology, the data points diverge. Okay, so we're actually capturing that. Okay, and both models are able to do a very good job of capturing that. Okay, below mu s, okay, you have the predictions actually are now more different. Okay, the cooperative gradient models have slightly different predictions. Okay, and in fact, Mehdi's model does a better job. Okay, so this is closer to the crappy data. Okay. These flows down here are so slow that our derivatives. This is essentially noise down here, I would argue. There is some evidence from the fact that we fit the data, okay, and then took its derivatives, that we actually have a divergence there as well. Okay, and again, these are the gradient model does a better job there.
What's on the axis?
So this is the diverging length scale, either of the solutions in Mehdi's model or what Ken calls the cooperative length, and it's squared and it's scaled by the particle diameter, squared. Okay.
I mean, if you just got those data and there's no predictions of divergent length scale, would you remotely think about?
Well, this side right here is okay. Leave the left side. The left side I wouldn't want to do any prediction on. Okay, but just on the right side, the data actually, just even with finite difference, has a diverging length scale there. I would argue those stars go up dramatically.
But the actual length is square root of this value.
Yes, the actual length scale is square root of this.
So somehow 3 of particle diameter.
It's not large. Yeah, it's not large.
3 particle diameters is divergence.
Well, it was, it's, okay, so let's not call it, okay, so let's,
In experiments, it often is. It's often is.
I mean, this is the reality. This is what the length scale is. This is what people call the diverging length scales. It's a small number. But I can't measure it closer and closer to there. I think is more importantly, is that I don't have the experimental resolution to go any higher. Yeah. So I think that this is a place where simulations are a much better place to test this than experiments.
You could easily say it's increasing.
I'll say it's increasing then.
Yeah.
Okay.
I mean,
I'm testing.
This is a rather strong word.
So, well, there's a question mark here. The prediction is that it diverges. And my answer is that what I observe within the experimental capabilities is consistent with that diverging prediction. I cannot observe the divergence itself.
It doesn't decrease.
Well, okay, but actually let me go over here. Let me go to the insight and look at Nico's question in a second. So because I have done this nice thing where I have interpolated my data, right? Okay, here's the interesting spot in the curve. Okay, this is mu s that I want, that's 0.6 that I want to be looking at. That's actually right in the middle of my data range. Okay, we got lucky. Okay, we got lucky. So I can take my 3 derivatives of it. Okay, and I can plot. So now you shouldn't look at the stars. You should just look at the blue curve. Okay, is 0 to 60? Are we allowed to call that growing a lot?
That's 0 to 60 in your fit.
It's not my fit. This is yeah. So 0 to 60 in the fit. So it's in between. It's somewhere in between model and experiment here. Okay. So from this blue line, okay, when I take my derivatives of it and put it back in the model, I get something that says that in reality, although I couldn't capture it because I don't have the experimental precision, it probably was rising quite a bit more. So this point here is at 10. That's this point right here. Okay. So what it says is that I can't measure any closer to that point. And I will never be able to. I will say that honestly. Like that I cannot do.
But what about if you can run the cell faster? If you get a larger...
Which is why I'm no longer running in this cell and I'm collaborating with people who have faster flows. Yeah. So
does that offer a possibility then of resolving this?
We'll see. Yep. We'll see. But I'm an experimentalist, so I haven't done the experiment. I say nothing about what its results are.
I would say if the cell goes faster, you expect that this length scale will be smaller. So you want to be in a regime where this velocity is as slow as you can, as small as you can. So you want to go to the regime where this I number goes to 0 actually. Mm-hmm. So I think that's the...
You think it's the best we're going to do. It's disappointing, but it's the best.
Slower, maybe you can
if we're just focused on these very slow flows, it seems to me, the mu-I rheology is a rate-dependent rheology. It says that the stress ratio is proportional to the shear rate. Mm-hmm. Okay? And it seems to me that might not be the right physics to use. More so like rate-independent plasticity should be applying in this regime.
It's still a valid question. Does this model able to capture these physics? That's still a valid question.
The second question is why?
Why?
Yeah, you're raising the right question. What is the mechanism that is controlling this non-local effect?
All right, so hold it.
Not only the non-local effects, also the fact that the homogeneous formulation has something to say.
Right. Predict the mu of I.
Right, that's true. Okay, so I have a couple more things to say on that before we get to the end. Okay. And yes, it does work that if I pick one set of parameters, okay, they work for all of the data sets that we tried. And this is over quite a large range. This is over the 10 to the minus 4 went away here. This is over 4 orders of magnitude in I, and it's over quite a large range in speeds. Okay, so both rheologies are able to do this. Okay, so from a practical standpoint, if you want to model your slow flow, right, you should feel perfectly comfortable using one of these rheologies, right? So that's a practical statement, okay, that they do a perfectly good job, right? Whether or not it is the one that captures the best physics and everything else, I would say that's an open question, okay? But it does perfectly well, okay? So we have had two.
I rejected the word perfectly, but.
Okay, it does well enough. Okay, take off perfectly. Seems fine. Seems fine by me. Okay, and that had not been demonstrated in experiments before. Okay, so let me be clear that that's not a small thing. Okay, So I have showed you two ways to get mu s. One was to just draw a line across here. That was crappy. Okay. That says that it's got to be something bigger than 0.26. Okay. And I called it 0.26. That was consistent with the maximum on this blue curve, which, by the way, I had no control over. That blue curve gave me that maximum there, and I had nothing I could do about it. Okay, so that's independent. So this is coming from taking derivatives of velocity profiles. Okay, and these are very close to each other. The maximum is very close to 0.26, actually. I think it's like 0.262. Okay, but this is about a yield stress. Shouldn't it have something to do with the forces? Right? Should have something to do with the forces. And now we come to the fact that this is a photoelastic system. Okay, and I can measure the forces. And if you haven't had a chance to play with these before, I'm going to pass this around. So these are the same particles that are in there. Okay, and if you squish on them and hold them up to the light, you'll see all sorts of pretty force chains. Okay, and if you like single particle approximations, here's the single particle one. Okay, and you can play with this one by yourself. Okay, so we'll start this on the other side. Okay. And so we can, in fact, and the resolution of this camera is not such that I can do fancy photoelastic fitting to get contact forces here. I'm doing something much dumber here. Well, I'm going to say how much are the force chains fluctuating here versus here versus here. Okay, just how much it's fluctuating. Okay, so imagine cutting this into rings of about 1 particle diameter. Okay. And for each one of those rings, I have a movie, and I say, what are the fluctuations of all of the pixels in that ring for the whole time that we had a movie? I'm just going to give you the magnitude of those. This is the crudest possible number. Okay, what I'm working on with Natalie and her student Amalia right now is that we're doing better jobs of characterizing those fluctuations. Okay, so there is something more here than I'm telling you. Okay, but this is what we know from first cut. Okay, so we do that. Okay, and here's what happens. So the inner wall is where there's very low fluidity. Okay, so even though the fluidity is, the inner wall is where there's very high fluidity. Okay, and as the fluidity is dropping, right, the fluctuations in the force chains are climbing dramatically. Okay, and at one point they absolutely plummet. Okay, and then the fluctuations are about the same near the outer part. Okay.
But we see rainbows all the way out. Look at it.
We see rainbows all the way out, but they're not fluctuating. They're much more static.
Oh, they just sit there.
They just sit there. They're boring.
They turn on and off.
Yeah, they kind of go. They don't do this.
But in peak they do.
But indeed, here they do. Okay, now I'm going to ask the question.
So where is the peak on the picture?
So the peak on the picture. Now here's the one annoying. So first of all, note this axis runs backwards, right? Because I wanted to do from inner to outer to match the picture. Okay, so this is low mu. So if I'm coming from here, what's the point at which, I cross to being in the local regime? That's 0.26. Okay, so this is not at 0.26. It's at 0.29. Okay, but I don't have a problem with that, and I'll tell you why. Okay, I didn't tell you something important about this experiment. So when we have the photoelastic particles, we have to put a lid on the experiment because we need to have a polarizer there. So I've just doubled the drag. Or probably not doubled it, but I've changed my boundary drag by sticking the photoelastic lid on it. Okay? And so I've raised the shear stress slightly. Okay, so instead of being at 0.26, this jump is at 0.29. And I can't tell you quantitatively that's correct because once the polarizer's on, I can't do particle tracking. So I have an either-or option. Okay.
But doesn't gravity keep the particles off that?
Oh, but guess what happens when you shear particles? They get all tippy and they start hitting the roof. Yeah. So the shear stresses are different with and without the roof. Okay. And so 0.26 and 0.29 are not the same number. I will also say that when we switch between 0.26 and 0.29 as parameters, we also really can't tell the difference that much.
Do the velocity profiles give you an indication of these two regimes?
They don't, actually. The velocity profile we found to be, so the green here is the velocity profile, okay, and the purple is the mu profile, and this is the point where it crosses mu s, and it's about partway down the velocity profile. I'll go back and show that to you. I had a better plot for showing that question. So there's mu s on the velocity profile. Does it look special?
Wouldn't you expect it to be, I mean, this mu-s is like a yield. I mean,
It's a yield criterion, yeah.
The standard mu of I
I need to wrap up, yeah.
is only for flow.
Right.
And you expect the mu of I curve to hit the
Yep.
hit the zero axis.
Yep.
And so this would be that mu might be the yield.
It could be, yep.
And then all of this behavior is below yield.
Right, but the important thing is that mu of I is not happening, mu s is not happening at an interesting spot in the velocity
So
profile.
I would say it might be at a point of inflection of the speed.
Yeah, can I say?
Yeah, I actually have to wrap up, so we're going to continue this discussion.
Can wrap up, and then those who want to
debate that.
go on and discuss
Right.
further can
All
do
right.
so.
Okay, so we are doing shape stuff, but I'm going to skip that except to say that shape changes the rheology. Shocker of shockers. Okay, and we're working on that now. All right, so enabled by the fact that we happen to have built these leaf springs for a completely different purpose, we were able to capture boundary stresses on a real experimental flow and took advantage of it. This allowed us to test the two non-local rheologies. They succeeded. Okay, there's a single set of parameters that works to do everything you want them to do, just like they do in simulations. We can actually see evidence of the growing, not divergent, length scale in US. The material parameters we found are consistent with what's been seen in DNAM simulations, so it seems like there's really good correspondence there. Okay, and that I think the new thing that we are contributing is that we really see that the mu-s seems to be associated with a plummeting of the force change fluctuations, and this, as a statistical physicist, looks a lot to me like a susceptibility, right? And so this is where Natalie and I are working right now, is to try to actually put that on firmer footing, where we actually measure things like temporal autocorrelations and things like that. All right, thanks.
Can you place what you've done in the context of Cameron and Cobalt's simulation?
And Medis.
What range of I?
I am slower, but not by horrible bits. I'm slower.
Okay.
I'm slower, and in part,
By a factor of 10, by a factor
yeah.
of
I'm gonna go pull up the plot because Ken's actually was precisely this geometry, and I don't want to get it wrong. So I am in 10 to the. I'm in this part of his and a bit lower. So I'm in here. So I'm seeing these curves here and a couple more, and I'm seeing mine actually crosses because it's not exactly the same. Yeah, but this is. I wanted to go slow because I'm interested in the creeping. I'm interested in the creeping regime. Yeah.
Yeah, so you're doing this association between this mu-s, or this correlation between this mu-s and the equation of the forces.
Mm-hmm.
So if I think of it coming from phase transition, so do you think that there is here a phase transition that is happening? And also, do you think that this mu of s is a material property of the system, or this is
This is precisely the questions I'm asking. This is exactly what I want to know. Yeah. So we saw a hallmark of something that looks vaguely like that, and the question is there any meat to that, or is it just fluff? I don't know.
Yeah, so the two models, they have these divergence of some perpetuity lengths close to mu-s, right? But then you say, well, if I measure an experiment, say, well, they diverge a bit, and then you say
it gets bigger.
You say later, well, I can also move mu-s from 0.26 and 0.29, and they do.
No, so they don't ruin the mu of I fits. They do mess this up badly, right? And so this is why I think the number is 0.26. Yeah, so I actually trust our measurements here that 0.26 is right, and I think the 0.29 is just because we have extra drag. That's falling in the wrong place.
What's your gut feeling? Do you think you need a divergence in the model, or do you?
I think you do.
Okay.
Yeah. So I think you, and I'm getting nods over here too. I think that you don't get the right information if you don't. The fits don't work. If I move mu-s too far away, the fits get really crappy. Yeah.
Well, the initial model that Camden had no divergence.
It did actually. It's there. He didn't measure it, but it was in the model.
He didn't measure what?
He didn't measure the divergence. No, actually, this is from the first paper. This is in the first paper. No, this isn't the first paper.
Hennen and Camden.
This is in it.
Have any divergence?
This is earlier. This is earlier. In the original paper, he measured the divergence.
Yeah.
It was in his very first paper. It was in his very first paper. The only difference is this model doesn't use a square root; it uses a 0.6 power. But it diverges just fine. Yeah. So no, it was in there from the beginning. Yeah.
So the length scale is a function of mu.
the length scale is a function of mu, and as you get closer to mu s, that length scale diverges. Now, what I'm interested in is what the physics of that is, right? So why does it diverge there? And so I would say that you guys have one explanation for it, Ken has another, and now I'm proposing a third one, which is that it's a susceptibility to force fluctuations, right? So I would say that the physical interpretation of this is extremely interesting.
Right, so I suggest that we close there because the time is up, but those who are interested can continue the discussion, and let's thank you.
Thanks.